Okay, I think we're ready to go. We are recording. Okay, so so today um, I'm going to start off with talking about quantitative MRI, quantitative T1, quantitative T2, because we've been talking about T1 weighted, T2 weighted, but we didn't actually come up with any numbers, because the images come back from the scanner, but they're not actually the T1 value or the T2 value. So before I talk about it, I just want to just sort of introduce some kind of motivation for it. So why bother with this sort of motivation? So the first part is what I just already said. So you get an image back. So here's an image of the brain, and that image has numbers in it. So what are those numbers? On the Siemens scanner, the numbers might be 400 integers that go from, say, 0 to 500, something like that. On another scanner, it might be numbers that go to 20,000. So those numbers don't have any specific meaning by themselves, and you can't compare them. So the first problem is you just have arbitrary values. Image brightnesses. And obviously, there's significant differences between those, like the gray and the white matter have different numbers, but there's no way that you can go and actually say that, because it was 400 in this guy and I scan somebody else and it's 500, there's actually a difference, because there's all different kinds of things that can affect those numbers, just the setting of the scanner, how the normalization of the analog to digital conversion was done on that particular day, how big your head is. There's a number of different things that can cause these numbers to vary. So in particular, there's no way that you can do the following. So you scan somebody 1 year, and then you come back the next year and scan them again, and then you actually can say, well, yeah, your brain has gone downhill. I was watching the video from last year. It's time to stop drinking, something like that. You can't actually sort of directly compare across time. And also, just as important, you can't compare across scanners, because scanners have different conventions. So if you had some way of actually estimating what the T2 was or the T1 number was, then that would be better, because then you could say, well, we've gone and we've seen a difference in the brain, or we can see that your brain is a little bit smaller or larger in this number than it should be. So that's the first motivation, to get some kind of quantitative number. But another motivation is there's uncorrected coil fall off. So if you scan somebody with an old style quadrature, really big head coil, this isn't too much of a problem, because the pickup generally is reasonably uniform. But even in that case, there can be a problem. Like if you're off center in the head coil, you're closer to the head coil, there could be a bigger signal on that side. But in the modern world, we've got these small coils in there, and those small coils pick up much better from where the coil is over. And as a result, if you're actually closer to the coil, the difference is bigger. So if you have a quadrature coil and you get closer to it, it doesn't make too much difference. because the pickup is relatively uniform. But the whole point of these coils, and the reason they have higher signal to noise, is that they don't pick up from the other parts of the brain. They don't pick up noise from other parts of the brain. And that's why the signal, which is the same as it would be for a quadrature coil, has a higher signal to noise, because it's not picking up noise from other parts of the brain. But that means that it's very sensitive to how far away from the coil it is. And so you can double or sometimes triple the signal by getting closer to one of these coils. And you'll often see, if you put somebody in the magnet in the 32 channel that has a big head, and their head touches up against the top of the coil, you'll see that the images from this part of the brain could be twice as bright as the images from some other part of the brain. So that's another big problem, and there's ways to try to fix that afterwards. So you can make some assumptions about what brightness the brain should be and then kind of normalize. There's all different complicated normalization schemes that people have developed. But obviously, if you had some quantitative number, if you were able to calculate a quantitative number, that would be a better thing than just trying to fix it afterwards without information. So what about B1 problems? So there's another problem, is that the transmit field, the transmit and the receive field is uncorrected. So B1, we'll say, let me just say uncorrected variations. So uncorrected variations in B1 transmit. So here we were talking about B1 receive. So this is B1, meaning the transverse magnetization as opposed to the longitudinal. So this is B1 receive. So for instance, this small receive coil is closer to the head, thereby gets a bigger signal. So that's from parts of the brain that are close by. So that's B1 receive. But there's another problem, which is B1 transmit. And in most cases nowadays, we're transmitting with the body coil. So that coil is relatively big. And that's a good thing, because that means it's going to have a relatively uniform, it's big and relatively far away from the body, and so it's going to be able to transmit a nice uniform signal throughout the bore. But that's not the problem. The problem is you put something in there. And so even though the coil is very big and uniform, when you put the head in there, the head, I draw it in the wrong axis, the head there, yes. There we go, there's the better brain. So when you put the brain in there, the brain will actually affect how the radio waves propagate through the bore. And this is especially a problem as you increase the field strength, because as you increase the field strength, what happens is, we know from the very first equation that the field strength is proportional to the frequency. So you increase the field strength, the frequency goes up, but that also means that the wavelength gets smaller. So the wavelength is inversely proportional to the frequency. So, and what's the wavelength is just like the space between, if you just imagine like you've got a very strong magnetic field and a weak magnetic field, strong magnetic field, weak magnetic field, it's this distance is the wavelength. That wavelength, if you look at a 1.5 T magnet, the wavelength is, a couple of feet. I don't know, 3 feet, something like that, between the wave fronts. So that's far enough, that's big enough compared to the head that the head doesn't affect it as much. But what happens is you shrink if you turn the frequency up, turn the Tesla up, which turns the frequency up, and then which causes the wavelength to go down, to get smaller, then it starts to get closer to the size of the head. And then what can happen is, it can be like your microwave. like you heat something up in the microwave and you get a little hot spot. One part's really hot and the other part's not as hot. And what that is caused by is these wavelengths sort of going in and interacting with the head as like a resonant cavity. And so different parts of the head can get different amounts of RF, even though if you didn't put anything in there, the radio waves going in there would be very uniform. So this is partly, it's not really caused by the by the coil. It's caused by the interaction between the coil and the actual electrical structure of the head. So unfortunately, that results in variable flip angle. And how much does that vary? It could vary by like 25%. So that means, like you said that you put in a 90, but instead you got like 120 or 115. Now, that doesn't seem like that much of a problem, but if you remember back to our that first assignment, when you plotted out the signal as a function of flip, what we're trying to do with these scans, we might be trying to distinguish these two, say, one was white matter and one was gray matter. So, and we, said, well, why don't we go here and, do that flip, and, to get good contrast between the gray and white matter. But if you have a 25% variation in the flip angle, it's possible, depending on what your flip angle is, you could even reverse the contrast in different parts of the brain if you accidentally sort of ended up over here instead of over here. So that's a really big problem, because that since the T1 contrast, so this is our signal in a fast gradient echo. So since our contrast is dependent in a fast gradient echo mainly on the flip angle, if it varies by 50% and we haven't measured it, then obviously that's not going to give us a very good number in different parts of the brain. So what are the actual numbers that we're trying to look at? Well, if we look at the white matter versus the gray matter, we might have something. So here's white matter, and so that's the first thing you would want to do is be able to distinguish the white matter from the gray matter. So the white matter might be say 110, gray matter might be say 85, something like that. If you have a nice something with really nice contrast, sometimes it's less than that, but we'll say say 105 and 85. So if we're messing around with the flip angle, we could easily get rid of some, we could easily overcome that. But that's still, we have enough contrast between gray and white matter where you can usually tell them apart. But what about looking at different parts of the cortex? So we know that, say, MT, for instance, is a myelinated area. And a myelinated area tends to look a little bit more like white matter, which means that it will be a little brighter. So instead of 85, it might be 88. So if you look across the cortex, what are the differences between different cortical areas? What are those? They're in the order of 1 to 4%. So MT might be 4% more myelinated than the least myelinated part of the brain. So so if we wanted to, for instance, measure the T1 values and then try to distinguish different areas on the basis of their T1 values, because those are going to be affected by the amount of myelination, so that we could, for instance, find areas. We're dealing with this very small difference, which could, the receive field is going up by a factor of 200%. Here we're looking for a 1.4, 1 to 4% difference. And the flip angle could even reverse the contrast, you know, so that could easily, it could reverse the contrast and change, like, you know, 85 into 105. So that gives you some motivation for why we want to try to derive some method that is a better, more quantitative method across the brain, as opposed to just trying to kind of post hoc fix the image. So that's the motivation for why we want to do this. Now you might wonder, why doesn't anybody do this? Because actually hardly anybody does this. And the general reason is that the only way you can do this is by collecting more data. So if we just have an image that has all these various distortions in it, we can try to fix it afterwards, but there's not enough information in there in that one number, because if you do an image, you just end up with a single number. You know, you end up with two numbers at each pixel, you know, which is the complex value, but you usually throw away the phase, and so you just end up with one number, and that's clearly not enough. So so what are ways of dealing with this? And so one way of dealing with it, so in general, you're going to have to somehow collect more data. And so one thing that we have set up on our magnet that automatically collects data for structural images is called pre-scan normalize, spelled with a British spelling. So what's pre-scan normalize? So the idea is, and so if you do it like an MP range on the magnet, you will in our protocols, this will by default be set up. And so what does it do? Well, it collects another scan. And so not only do you have to collect another scan in order to try to solve this problem, but you need to collect a scan with different parameters somehow. Because if you just collect another copy of the scan where you got two numbers, you can average them, but it's basically still one number. So how does this work? So this basically collects an image with a body coil first. So if you collect, so what does this do? So this allows you to basically correct for what you're trying to do. What the goal is to correct for the coil fall off problem. So if you collect with the body coil is far away. The signal isn't very good, and so typically, for a standard scan, you would, standard, structural scan, you would do, body transmit, and, local coil receive. So you would get that on the receive side of the B1, you would get that extra bright image. But the transmit would be as uniform as it could be, still have some B1 problem, transmit problem. But what if you just collect an image with the body coil? So you wouldn't use that image for normally, because the signal to noise is much lower than the local channels, the local receive coils. But that is going to be far enough away that it won't have any of the B1 receive problems. So it's far enough away from the head so that the brightness of the image will be pretty much the same. And then you could, set parameters for low gray-white, gray matter, white matter contrast. So if you set parameters so that there's no distinction between the low and white matter, then basically you can try to get an estimate of what the receive fall off is. So the idea is if you had high gray white matter contrast, then as you go to different parts of the brain, the signal varies, but some of that could be from gray white matter contrast. So if you just do a scan that has low gray white matter contrast, then that's how you could sort of more easily estimate what the fall off is. And this is, it's relatively smooth. So that's good. So we don't have to do a high resolution scan. So what that means is if you look across the head, there's going to be variation. So this guy will be a little brighter over here because it's next to the coil, and then it gets a little darker, and then this guy gets a little brighter. So that if you plot, if you plot the field through there, what you're going to get is something that's this relatively smooth variations. It won't it won't do something like that and then change. So because it's relatively smooth, you don't have to collect a you can collect a low res. Obviously, the problem with all these schemes is that they all have to collect more data, and so that means more time. And as soon as you get more time, then you could get movement artifact, all different other kinds of problems. So you only need to collect a low resolution scan, and then basically you can divide your T1 scan by pre-scan. It's more complicated than that, but that's roughly, you can sort of think of it that's what's going on. So basically you divide out these variations. So if the real scan is big, the pre-scan will be big too. If the real scan is small, the pre-scan will be small too. And so then when you divide, you'll end up with a uniform image. So if you run one of these scans, you'll hear this scan run at the very beginning. It's a high-pitched scan that runs at the beginning. It only takes about, I think 5 seconds or something like that, 8 seconds. So all these things have to be optimized so that they don't take much time. So it takes like about 8 seconds. You'll hear this little high-pitched scan run right before the main scan runs. There'll be another scan. There'll be 2 high-pitched scans that run. The first one is a shim scan, and I haven't talked about that yet. We'll talk about that next week. But this is yet another one, another pre-scan that runs. And so this is a very useful way to do it, because it's always better, an aphorism, it's always better to collect more data and have more data than to try to fix up bad data. And so I think this is generally a very good thing to do. And so we by default have this on. So the principle here is we're collecting a second data set through a different coil, and then we can use it to try to normalize. It's not really quantitative T1, but at least it gets rid of most of the coil fall off problem. So that's pre-scan normalize. So another very similar thing that was done in the human connectome project is T1 divided by T2. So the idea here is very similar, is that you basically, so you collect an MP range and then collect one of those space scans. So the space scan, a T2 weighted space scan, you can get a proton density weighted one too, but you collect a T2 weighted. So this is T2, or T2 star actually. And this guy, that's right, spin echo, so it's T2. And this one is T1. And so if you look at the space scan, there'll be almost no gray-white matter contrast in it at all. And so so if you just divide by that, you'll end up again with a number that gets rid of, it removes coil fall off. So it doesn't deal with the So there's several issues here. So it removes coil fall off. It doesn't correct the B1 transmit problem, because the transmit field is going to be non-uniform, and then the transmit field affects the value that you get for T1, because this is a fast gradient echo. The other problem is that this is a T2 weighted scan, whereas this guy is a T2 star type scan. And so you'll have different distortion. So that's another issue, especially if you're dividing one by the other. So the T2 mechanism, the spin echo mechanism, because the space scan is basically a fast spin echo, will correct inhomogeneities due to static field offsets. And that will actually then fix some of the spatial distortions, which we haven't talked about. Talk about that next week. It'll fix some of the spatial distortions that will appear in this T1 scan. And so and if you're dividing one by the other, and they're slightly differently oriented, then that could be a problem. But you're generally saved by the fact that the fall-off field is relatively smooth. So so that's another thing you can do. Now, what's yet another one? So yet another one is MP2 rage. And so we have this one on the scanner also. You can try this one. So you got a 2 in there, so there must be you must be collecting some additional data. So what you do here is you collect data that's actually 2 different inversion times. So what does that look like? So you collect 2 complete sets of data. 2 complete sets of, so this is a 3D fast spin echo. Sorry, fast gradient echo. And so it starts off with an adiabatic pulse. And so what is the sort of adiabatic pulse? I'll talk about this one again when we talk about perfusion imaging, but an adiabatic pulse is one of the best. If you have a lot of time, it's one of the best ways to do a good quality 180. So this is a good 180. So the adiabatic pulse, it's instead of doing something like a sync function that sort of emits a narrow range of frequencies, what it is it's actually much simpler, and it sort of goes way back. You just transmit a single frequency and just slowly ramp the frequency of the transmitter. So what you do is, if this, over time, you just ramp the frequency of the transmitter like this. This is time. And here is the resonant frequency. So this is, lar more resonant frequency. So it's unbelievably simple. You just go just ramp up the frequency of the transmitter, and going through the actual frequency, which is defined by whatever the B0 field is. And it turns out that, amazingly, we'll talk about that, how that actually works, that will do an extremely good 180. The reason that it's not normally done is because it takes a long time. But since this is an MP rage, there's always going to be a gap, because you remember when you run an MP rage, you'll hear that little gap and then a whole bunch of data collection, and so you got time. So if there's time anyway, time to kill, you just have to wait for the spins to start to recover. Then you can do one of these because it takes longer. So you just do one of those, and it's a 3D scan. So if we draw out the other gradients, so here's the RF, and here's the Z, Y, and X. So we wait a while, so I'll put a little gap in there. So we wait a while, so we do this is the inversion pulse. That's the PMP, magnetization preparation. That's what the what this preparation pulse is. And then we start doing a bunch of little alpha flips. And so here I'll just draw 3 of them. So this is this forest of like 100 lines of K-space. And so during, and these could just, I drew them as sync pulses, but we could just do hard pulses because it will just be quicker. So we'll just do a bunch of little short hard pulses because we just did a nice inversion here. So then what happens is we are going to do our, like a standard, so these are all, everything's all jammed together. So here's our readout, like that. And then our phasing code will be here. So here's all the different phasing code steps. And it turns out when I read this, I just read this paper last year. It's a paper from 2010, but I finally just read it. They actually do something that's a little bit more like a fast spin echo. They kind of fix the, so they do phasing code that way, and then after they're done, they kind of fix it. So it's almost like a steady state type gradient echo. Because remember, we had there was grass, which was where you fix the magnetization, and then there was spoiled grass, where you somehow try to put another gradient on to mess it up, or put an RF pulse on with a different phase. So in this case, we're sort of doing something a little bit like grass. But you'd think the contrast would be different, but it turns out the biggest determinant of the contrast is when you get to the center of K-space. And so after a while, we eventually get to the center of K-space, and that won't have any gradients on. So, so here's the RF signal, so there'll be a little echo here, and another echo here. And then when we get to the center of K-space, there'll be no phasing code gradient on. And so that one won't be kind of a steady state one. And that's the biggest echo as you go through the center of K-space. And that affects the contrast the most. So it still has a contrast that looks like a spoiled gradient echo. So far we haven't done anything different except we just kind of put the gradients back. So here's another different phasing code step, and it's going up and down. But it's a 3D scan, and so a 3D scan means that we've also got to do this business on the z-axis, because we're collecting 16 million data points, or in this case we're collecting 32 million data points because we're doing 2 of these eventually. Okay, so this was the first. So this guy is the RF record. So definition of the inversion time, so this guy to when we record, so this is the time of inversion 1. Time of inversion 1. So this is the center of K-space. So we collect a whole set of data, and then we collect a whole another set of data. So then, you know, we finish up collecting one partition. So remember, this is the partition direction. So these gradients would be for one partition. These would all be the same, and then we would cycle through all the different possible combinations of phasing code. So this is phasing code direction, and this guy is the partition direction. So we would have to just pick a particular setting of the partition gradient, go through all the possible combinations of phase, pick another one, go through all the possible combinations of phase. So so we do like 100 readouts here to get a whole bunch of lines of K-space, and then we just collect another one. So now there's a whole nother one. So basically the same thing over here. So just go again with, you know, the same set, you know, pick one partition, go through all the possible combinations of phasing code, do, you know, a zillion readouts. And so what will happen, and then when you get to the center of K-space, so like, you know, after a while, we eventually get to the center of K-space, and so here's the center of K-space. So center of K-space 1, so this is the center of K-space 2. That will define our second time of inversion. So this is, you know, time of, you know, inversion 2. So so what we'll end up with is 2 complete 3D data sets just for one scan. And so then what do we do? So then what you can do, and the first one will look more or less proton density weighted because of the short inversion time, and the second one will look a lot more T1 weighted. And so you can just do a slightly more complicated version of dividing one by the other. And so what they do, what our scanner will put out is, if I erase this, it just puts out the 2 images separately, but then it puts out an image that combines them and gives you something that has a quantitative number. And because of weird patent restrictions, we can't get the T1 value and the proton density value out of the scanner. We have to run some MATLAB code, which is freely available, but the scanner itself doesn't do it. But here's what the actual scanner calculates. It takes the complex conjugate of the signal for TI1 and multiplies it by the not complex conjugate of the signal. So this is the complex valued signal, and when we're multiplying if we want to square a complex number, you'll often multiply it by the complex conjugate, which will sort of cancel out. You can sort of think of it as, you know, A plus B times A minus B. That will sort of get rid of the it will get rid of the 2ab that you would get, and you'll just have, you know, a squared minus b squared. So that's sort of a quick and dirty explanation why when we're multiplying two complex numbers, we often want to take the complex conjugate of the first one. So we multiply these guys together. So this is ti, the signal from this second one, times the signal from the first one, and then divide that by the amplitude of those signals. So this means I take the amplitude of that signal of, you know, ti1 squared plus the amplitude of the second signal. And this is a convenient ti2. So when you do that, well, if you just look at how that works, like, you know, a times b over, you know, a squared plus b squared. This is like, you know, signal squared over signal squared. What you're going to get is this will go from minus 0.5 to 0.5. That number will be in that range. And then what you can do is, you know, run some MATLAB and calculate actual T1. Actual T1. So that's so this is a way of trying to actually get a more quantitative number. Now, one of the things that when people first look at these images, they'll say, yeah, okay, but, you know, what's all that noise? So if you look at an image of a brain like this, the brain will look great, very uniform, because you've essentially, by combining these signals, you got rid of all the T1, the B1, the B1 fall off problems, because you're sort of comparing two signals that have the same fall off in them. But if you look out in the air just looks like complete noise. And in fact, not only that, the skull looks like complete noise. So if we look at you know, here's the brain in here. And you've got the CSF, which is dark. So the CSF will look like noise. It won't look black. And then you've got some marrow of the bone. The marrow of the bone will look correct, but if you actually look at the CSF, it'll just be all speckly. And the inner table of bone will be speckly. And the outer table of bone will be speckly. And then suddenly you'll be able to see the skin again. So then there's a little bit of fat on top and then skin on top of that. And then when you get out into those will look okay. And then when you get out into the air will be completely speckly. So why is that? So the problem with that is the signal from the CSF, the inner table of bone, the outer table of bone, and the air is very, very small. And so when you take a very, very small noisy signal and do this to it, you get a noisy number. So that's another reason why people haven't used these as much, because when you do this calculation out in the air, so if we go back, why is the air black in the first place? The air is black in the first place because the number out in the air is very small, because there's not very many protons, because the proton density of the air, you know, like, so if we have a normal brain image, you know, the brain is bright, but the air around there is completely black. So, you know, why is the air black? No signal. Now, it doesn't mean there's no signal. There's actually a little signal, so there might be like 1 or 2 or 3 or something like that. So there actually is a little signal coming out of there, but it's a very noisy signal. And so when you take two noisy signals and do something to them, you just get noise instead of black. And so when you have one of these images, you've got to do a little additional work. You could go back to one of the images, the individual images, and try to figure out where the air is, and then use the individual images to essentially blacken out the error, because you can just see how, you know, what that value is in the individual images. But it requires a little bit of additional processing. But the big advantage of it is it's completely taken out all these coil fall off problems. So that's MP2 Rage. So we have that on the scanner. You can run that. And then last but not least, there's another version that I'll talk about in more detail next Friday AM lecture. So basically we talked about pre-scan normalize. That was collect an image through the body coil and then compare that to an image through the head coil. There was T1 divided by T2, like they do with the HCP. That's collect a T1 and a T2 image and, you know, divide them by each other. Then there's MP2 Rage, which is collect two complete images, 3D images that have two different inversion times and do something to them. And then there's the one that I was involved with. I didn't do the conceptual part of this. I just used it. But you could also collect two flip angles. And so what's the idea here? So the idea here is that we do you know, our standard fast gradient echo, and you know, which is flash, so not MP Rage, just regular flash, no preparation here. This is the preparation pulse. So don't do that. Just do regular flash, but with two flip angles. So two separate scans. So two separate complete scans. Yeah. Two separate scans, and then so if we draw out the signal amplitude that we used in the homework, it was like 1 minus e to the minus tr over t1, and that was over 1 minus cosine of the flip angle times e to the minus tr over t1. And then it was multiplied by e to the minus te over t2. So that's kind of a complicated equation. We have two equations like this now because we collected two scans. And so potentially we could try to, sorry, I forgot the proton density. So here's, we'll put PD here, and proton density in there. So if we just throw out this guy temporarily, we'll say how we could fix that. And then we've got two unknowns. So we have proton density and T1. So if we just have one signal with two unknowns, then obviously we can't distinguish proton density from T1. There's another unknown here, but we threw it out for now. So, however, if you've got two scans like this with different flip angles, this is the flip angle here, then you have two equations. You can solve two simultaneous equations and figure out proton density in T1. And so that's basically the way this method works. So you collect two images, and then you effectively have two copies of this equation. And with two copies of the equation, then it's possible to actually simultaneously solve them and figure out what the proton density is and what the T1 is. And I'll talk about this in more detail, but it turns out this is the most amazing thing to me. So it turns out, oh, I forgot the sign in here. There's proton density times sine of alpha. Sorry about that. One minus, yeah, there's a sine of alpha in there. Okay, it turns out that equation, this equation, is virtually identical for low flip angles to the following equation, which doesn't even look anything like it. So just the flip angle times TR over T1 divided by the flip angle squared divided by 2 plus TR over T1. You just have to actually go in MATLAB and plot out these two equations. They'll just lie completely on top of each other. They don't look anything like each other. And how do you do this? Well, I mean, how do they come up with this? The idea is we analyze this equation that has all these exponentials in it, but we sort of break it up into a series, throw away the later terms in the series. And so, if you look at something like a cosine, or a sine, if you look at something like a sine, it starts off quite flat. And so you can basically sort of approximate that by a line. And if you look at a cosine, a cosine also starts off, if your flip angle is low, cosine is not any different than 1. And so you can just kind of throw out this cosine, and the sine can be approximated by just the slope of a line. So this one is a linear equation without all the exponentials in it. And so then we can just solve two simultaneous linear equations for two unknowns. So we'll have two signals, and then we've got two unknowns here. I forgot the proton density in there. Yeah. Okay. Yeah, proton density. So here's the other unknown. Okay, so I'll go over that in more detail, how that actually works. But the bottom line is that you could eventually end up with a quantitative proton density, quantitative T1. You still have the problem of all the speckling in the air, but again, you could just go back to the individual images and try to figure out where the air actually is. And the speckling, again, comes from the fact that you're taking two very noisy signals and interacting with each other, and then you get noise out of that. Okay, so we'll end there. Thank you for that, David, and then ask for some questions.